Okay, welcome to our review session for STA317G. I am Jared, and today we're going to be reviewing some stuff about multiple regression, much of which will be review, and we'll cover a few concepts from this week as well. So, can everyone see the code okay, or should I make it larger font? We can go larger. All right. This first line is just a suggestion that you get on all of your homeworks to change the output from a few digits to several digits. And then for the data set this week, I'm going to pull a data set from my PhD advisor. His website has a data set on used car prices. I believe they're of Mercedes. So you can type this in, or if you just go to the website, you can download it and then load it in with the read.csv command if you want to follow along. If not, you're free to just watch. Okay. So if we want to create a multiple regression model, that is, if we want to have a regression model with multiple x's, as we've seen before, you just have your y variable. So let's say we're going to try to estimate the price of these cars based off of their mileage, the year the car was made, and the feature count, how many features the car has beyond the standard base package. Okay, so run that line of code. We have our model 1. With all models, we can look at a model summary. Here's where the font shrinking is detrimental for us. It's harder to read, so I'll zoom out a little bit. Here we have the summary table that I hope you've seen a few times. We have our estimate of the coefficients, both the intercept and the beta hats, or the coefficients for each of our x terms, each of our predictors. Okay? Yes? Not a problem. So, a quick way to get the plots you need for testing the regression assumptions is just to ask R for a plot of the model. What this does is you'll notice that the command line now reads to hit return to see the next plot. So this is a little funky compared to most R things, but it may save you time. So if you click just enter in the command line, it'll bring up the first plot. This is your residual plot, right? You've got residuals on the y-axis, and we often put an x variable on the x-axis, except now we have multiple x variables, so we're going to put the fitted values now instead. What do you notice from this residual plot? Does that look good or something wrong? Residual plot hopefully has points equally spread around the 0 line, which is this faint dotted line here. Instead of that, we have more points over the line on this side and under the line on this side, general curvature, and the variance increases as we go from left to right. So this model is effectively both, well, it has issues with both linearity and heteroscedasticity, or non-equal variance. Now, if we hit enter again, we get the QQ plot of the residuals. And here we see that the points don't quite follow the line, which means we have some normality problems as well. There's two more plots in this sequence that we don't really cover for this course, so don't worry about them. The ones you really want are the first one, which is your residual plot. If I go back here, use the residual plot to check linearity and equivariance. And the QQ plot can be used to check normality. Similarly, you can just use a histogram of your residuals to check normality as well. So we need to fix some things about the model. The other thing we need to pay attention to in the model is the year of a car and the mileage of a car are going to be heavily correlated, right? If it's a car that's being used, every year or so the car will probably put on about 10,000 miles. So what we probably really want is an interaction between the two, which will allow us to not just compensate for differences in years and mileage, but to account for cars that aren't driven as often. Maybe it's a showroom car or something, or cars that are new and driven a lot. This will allow the model to account for those. So to put an interaction in the model, instead of the plus sign, we include an asterisk. What the asterisk will do, I'll run these lines here, it includes both mileage and year, as well as the interaction between them. And now if we look at the plots for Model 2, we see it's a little, maybe better, but we still have variance problems and some linearity issues, and normality still struggles. All right, so slightly better with adding the interaction, definitely more interpretable because it follows the notions of car driving and prices. But the theme of this week in class, hopefully you've heard about transformations, and that's what we'll be talking about now. So one of the things we can do to fix a residual plot that looks like this, right, where you've got this like horn shape, it looks like a elephant tusk or something, right, pointing on one side, fans out on the other one with both linearity problem and equivariance problem. If you recall in the slides, it suggests if you have multiple problems, try transforming your y variable. So let's transform the y variable. We're going to take the natural log, which in R is just log, in case you ever need a different base for your log in R. That's an argument you can put into this function. We're going to take the ln of price, we'll call it price ln, and create a new model. The same interaction plus the features. See, everything is still very significant in the summary. But now we can look at the features. So we're going to step through these four plots. And again, just really pay attention to the first two. All right. How does that residual plot look compared to the other ones? What do you think? Yeah, quite a bit better, right? We don't see really any curvature, and more or less the variance is equal across all fitted values across the x-axis. This is an acceptable residual plot. If we look at the normal QQ plot, we still have some issues with the tails, but you'll have a little bit of that regardless of the model if you're using real-world data. Later on in my presentation today, we'll be looking at how to read a QQ plot. Go through several examples. All right, and recall these last two we don't analyze in this class particularly. So, an important thing to know, what's the inverse function of a log? So if I take the log of price, I'm now going to know the log price of all of these cars. Most people aren't very interested in what the log price of something is. They probably want to know what the actual price is. So to undo a log, we use the exp function. Really, we're taking e to a power, and that's just called exp. So if I take the exp, if I exponentiate the logarithm of 0.45, I just get 0.45 back. Okay, so if I get a log price out of my Model 3 here, I can just exponentiate it, exp function, and that'll get me to a real price as opposed to a log price. Does that make sense? Similarly, as you discussed in class, you could take the square root of your car price, and then we could model that square root instead of the log, or the unaffected, or the untransformed. So if we look at this model, it's also very significant and pretty good R-squared. But in this case, if we look at the plots, it's not quite as good as the log transformation. We see nonlinearity in the left tail here. And this jump come back to the QQ plot. So in this case, taking the log transform of y is preferable to the square root. Any questions? Yes?
So you're saying that that's preferable because it's more alternative.
Yes. So if I scroll back here, recall that, so this is the square root model. It's got a bump right here in the normal QQ, and there's quite a few points that are straying from the line of perfection. And the residuals here are showing some nonlinearity in the tail. If we go back to the log model, the jump in the tail here is not as extreme. And also this is much more equal variance and doesn't show any signs of tailing off linearity. Perhaps a tiny bit in the tail, but it fits the assumptions much better. And to boot, if we scroll up and look at like the R-squareds, this one's 94.8% R-squared, whereas the square root model is only 92.7. The model fits better and follows the assumptions better. Cool. One of the things that comes up frequently is using this model to make predictions. Any model can give you a single point prediction of what they think will happen, but really we're not sure that the value is going to be any particular single value. So we want to get an interval instead. So let's say I've got a car that has 200,000 miles. It's from 1985, and it only has 14 features. What is a reasonable 95% interval for the price of this particular car when it sells? Well, this comes back to tell me that the target value is about 94,000, and my prediction interval is anywhere from 61,000 to 127,000. So a car with these given numbers, 200,000 miles, built in 1985, 14 features, could sell reasonably anywhere from 61,000 to 127,000. Now, the confidence interval is not an interval for a particular car. It's an interval for the average price for that particular car. So I put in an extra word, right? It's an interval for the average price, not just an interval for the price. So now if I type confidence, this interval is going to be much smaller because this represents my uncertainty about the average, not my uncertainty about the randomness in prices. Okay, this makes sense because this is really showing how much I trust the model versus how much variance there is in the data. The prediction interval takes into account the whole variance of the data. Confidence interval is just looking about the variance along the line, or in this case, the variance for this average car with these features. So just be aware there's two types of intervals. Right? Covered this before, but This is called the R review session, right? Okay, so the next thought for you, having just discussed the predict function, if we have an interaction term between miles and year, as we do in Model 3 and 4, given a certain change, let's say you want to look at what the effect of taking your car on a road trip would do to the price of your car. So let's say we've got a car and we want to put an extra 1,000 miles on it. What will that do to the price? Well, before we put an interaction term in, that's pretty easy to figure out. You just look at the coefficient or the slope on mileage times how many miles you want to put on the car. You're done. When we have an interaction term, it's a little trickier. Now you can definitely still do it by hand with algebra, or we can look at it using the predict function. And this will come in handy on the homework as well. So let's take this classic car. Let's say it's got 200,000 miles on it, built in 1960, and again with 14 features. So this is the price of my classic car. Let's say it's worth $213,000. It's a really fancy car to take on a road trip. So let's say I take it on a road trip and I increase the mileage from 200,000 to 201,000. Okay, road trip is now the value, the forecasted value of the car after the road trip. So if I take the classic, which is the pre-road trip value, minus the post-road trip value, that would give me the amount of value my car lost, right? And in this case, we would anticipate that it's worth more before the road trip than after. However, we get a negative number, which means that after the road trip, it was worth $3,000 more than before the road trip. Does that make any sense? Sure, I agree. The problem is, that's the age of the car as opposed to the use and wear and tear of the car, right?
So we're not basing it off of years?
Yeah, the year is accounted for, but the year is accounted for in both cases. Right, if I put 1,000 miles on a car in a week, we would expect the value to go down because I just put wear and tear on the vehicle. Well, this is what I have explained here as a side note. Notice if we look at the summary of the cars, this gives us some summary statistics for each of the variables. Notice what years our data set contains. 1988 through 2015. If I put in a 1960 car, will the price of a 1960 vehicle be represented well by this model? No. The model is only familiar with cars built between 1988 and 2015. Trying to understand the age of a 1960 car is what we call extrapolation, meaning going beyond the natural range of the data to try to make guesses about what's going on. That's a side note. That's not part of this week's homework. But if you see weird things coming from a model, one of your thoughts could be, is this model appropriate? So for example, if I take year and mileage and make a scatter plot of those two, we can see here, yeah, we have one car from 1988, and really everything is from 1994 to present. So a 1960 car will not be well represented. We don't know anything about what's going on back then.
So how do I get these values?
Oh, no, just type in the classic. Okay. That concludes any new principles for this week, but I've built some practice for looking at plots. If you're typing along, I wouldn't worry about following the code at this point so much as following the graphs. Unless anyone has any questions about cars. Or the cars. What I'm going to do here is make my plot much larger so we can do some discussions about normality. One of the questions I often receive is how to interpret a QQ plot and what deviations from 45-degree line are okay and which aren't. I thought this could be useful. So to do this, I'm going to look at both the histograms and the QQ plots. And there's a command in R. I can change the graphing parameters to allow me to put two plots in side by side. So the first thing to show you is something that's obviously not normal. If I take some heavily right skewed data, this is the histogram. You can tell easily from the histogram that that's not normal. And in the QQ plot, you can see that as well. Right? We see that this doesn't follow the line, and really it's just bent. It's not straight, so it's not normal. Yes? F row, is it inside the par function? So you can type this along if you want. I'll be going through it fairly quickly, and the code will be posted later if that's okay. Okay, great. All right, so clearly not normal. Let's look at some examples of what is normal, just to see what deviations from that 45-degree line are tolerable. Okay, so here's some random normal data set size 20. But if I rerun this over and over again, you can see that sometimes it doesn't follow the line as much as we'd like it to, but this data is in fact normal by construction. Part of this is a problem because it's a small data set, only 20 points. You can see usually normal data follows the 45-degree line, right? So let's increase the data set size to 50. Once again, this is truly normal data, but because of randomness, sometimes we get stray points at the end of the QQ plot, right? What my goal is to show you today is if it's only a few points, I mean if it's only a small percentage of the data that's straying, we're still good to call each of these normal. Well, because in fact they are normal, right? Okay, so now that we've looked at several normal examples, here's some things that aren't quite normal. Notice in this plot, we don't just have points that are kind of off the line, we have a consistent pattern, a tail of points ranging off the line. Right? This is a pattern. We're moving away, and the normal ones would kind of start to come back. It wouldn't as a pattern, move away together. So this is, I've created normal data with slight skew. So it look mostly normal, but we'll see some skew in the tails like this. And I'm just rerunning the same code over and over again just to show different random data sets. This one's extreme, right? You can see that this tail here in the histogram shows up in the QQ plot like this. All right, this is with skewed data. What if it's not skewed? What if it's just too high variance? What if it or not high variance, too high kurtosis, if you remember that word from 309. This is what outliers look like, right? Let's get one without an extreme outlier. So here we have data that is symmetric, right? The peak's in the middle, the tails are about the same size, so it's not skewed, but you can see this extreme jumps on the tails might lead us to think that this isn't quite normal. As we can see here, right, once again, it's basically, minus this outlier, we're basically symmetric, unimodal. However, very few of these points sit on the line. They start to deviate, right? Okay, so none of these are normal. That one looks not too bad, but once again, at its heart is not normal. Okay? Any questions on interpreting QQ plots? That's my example for today. We can also look at equal variance. So we're going to change the graphing parameter back to a single graph. I'm going to show you some residual plots that I've, well, specifically constructed to demonstrate some points. equivariance? Or no? Definitely not, right? Here there's basically no variance, here there's high variance, and it just makes a giant bell-shaped curve, or bell-shaped range as we increase in x. All right, so I say this here has an obvious problem. What about a less obvious problem? It's not as stark, but we can see that if we look at the far left range of the plot and the far right range of the plot, there's a consistent increasing variance. All right, this is this is half of the horn. The other part of the horn is it's not linear. So this is linear. All right, the average line would go straight down the middle, but we're increasing like a megaphone. How about now? Perhaps a slight problem with decreasing variance? You could certainly argue that there's no problem here. This one has a little more of that issue. But. All right, what about something that is truly equal variance? Right, this is kind of the ideal. There's no clear pattern going on anywhere. There's about basically equal spread, minus 1 or 2 points that are, like the guy on the top, he's a little unusual, but we couldn't call that an outlier because he's not really that extreme. This is the prototypical example of what we want to see. Right? These are all wonderful examples. What's also okay, but perhaps a little more daunting, are these, right? So I've literally taken random x values and random y values. They're both centered in the same spot. So the spread is, let me rephrase that. There are fewer points as x gets further from the center, right? There's more points in the center than the outside, but in general, the spread is the same everywhere. There just happens to be more data in the middle. So this is equal variance, but we just need to notice that, yes, the points are more concentrated here and not as concentrated out here, even though the spread is basically the same. I feel like that didn't make sense. Did that make sense? Good enough? One last example on equal variance. What if we don't have much data? The less data we have, the less the less conclusive we can be. All right, these are all perfectly tolerable, but just doesn't have as many points. Okay. All right, last thing, linearity. Let's go to a double plot. Okay, so in this case, the left plot is just a scatter plot of x versus y. Looks like we'd be pretty good to use a linear regression model, right? However, what we can't see in the scatter plot, we can definitely see in the residual plot, which is to say there is slight curvature here that we don't see automatically, but when we plot the residuals, we definitely have a linearity problem, right? This would need probably a quadratic model, a slight parabola to fit that correctly. All right. There we go. That's a slightly better example. Here, the same problem. This looks straight. But if you look at the residuals, this isn't as extreme as the previous one, but our average is definitely curved. Okay? Linearity problem. This is the perfect example. There is no problem. It is, by construction, a linear relationship. And in the plot, we see no deviations from what would be the center. Right? So if I draw a line straight through the center of the points, that line is flat. That's exactly what we want in the residual plot. One last example. Here we have a perfect residual plot, right? Nothing going on. However, so we don't have any problems with linearity, but frankly, if you look at the scatter plot, there is no relationship to begin with. That's not something to be overly concerned about, but I just thought it might be interesting to see after all these plots. So you can meet the regression assumptions and not have a significant regression. That's why we check both the summary, we look at the R squared, we check the plots, get the whole picture so that you understand what you're doing as the researcher. So, pop quiz, quote unquote. What conditions are violated here? What do you think?
Is that linearity tested out?
Right here?
Yeah.
So this one we check for normality.
Oh.
If there's a severe linearity problem, it'll show up everywhere. But yes, to your point, that is nowhere near linear, right? This doesn't fit the line. So this line represents normality, and this is very wonky, right? So we have an extreme normality problem. Anything else violated? Well, our variance is approximately equal, and our linearity is not too bad. The actual model itself is not linear. But sometimes we have to look at plots and say, you know, there could be different violations. Which one's worst? Which one do I start fixing first? And in this case, normality's horrible. Okay? Last things last. For your own sake, I would suggest at this point using the par mfrho equals C11 function, which turns your plots back to a single graph per box, as opposed to double. Otherwise, you'll be very surprised next time you try to plot something, because I do that to myself. Thanks for coming today, and I can take any questions you have.